For years, I believed a very specific piece of science fiction was, deep down, real physics wearing a costume. Two particles get entangled. You separate them. One stays on Earth. One goes to the far side of the galaxy. You measure one, and the other instantly knows, no matter the distance, faster than light could ever cross the gap. I pictured it as a kind of cosmic walkie-talkie. Flip a switch here, the message arrives there, instantly. Physics quietly allowing the one thing Einstein spent his whole career forbidding. I picked this up from the same places most people do. A movie where a scientist taps a glowing particle and a twin particle across the galaxy lights up in perfect sync, presented as a loophole physics forgot to close. A comment section insisting governments are already using it for instant battlefield communication, kept quiet for obvious reasons. None of it ever came with a mechanism attached. It just arrived pre-packaged as quantum, a word that in casual use has become a synonym for anything now being allowed. I have to walk that back completely, and I mean all of it. Entanglement is real. It is arguably the strangest confirmed fact in the whole of physics, stranger than black holes, stranger than time dilation. And it has never, not once, in any experiment ever run, anywhere on Earth or in orbit, sent a single bit of information anywhere. That sentence sounds like it should be a contradiction. Something can be spookier than anything else nature has ever produced, and simultaneously useless for sending a message. Both halves are true, and by the end of this video you're going to understand exactly why, because the resolution is one of the most elegant pieces of reasoning in modern science, and almost nobody explains the actual mechanism. They explain the spookiness, show you the headline, quote the Nobel Prize, and stop right before the part that actually makes it make sense. Let's start where the whole argument started, with the man who invented the phrase people still use to dismiss it. In 1935, Albert Einstein, along with two younger physicists, Boris Podolsky and Nathan Rosen, published a paper meant to be a knockout blow against the new quantum theory. Not an attack on the mathematics, which worked perfectly and predicted experimental results with uncanny accuracy. An attack on what the mathematics seemed to be claiming about reality itself. Quantum mechanics, as it had been formulated by Bohr, Heisenberg, and others in the preceding decade, said something deeply uncomfortable. A particle does not have a definite property, like its exact spin or its exact position, until that property is actually measured. Before measurement, it exists in a genuine mixture of possibilities, not merely an unknown to us value, but an unsettled one. Einstein found this intolerable. He believed, the way most people instinctively believe, that things have definite properties whether or not anyone is looking. The moon exists, he liked to say, even when nobody is watching it. Einstein, Podolsky, and Rosen constructed a thought experiment, now universally known by their initials as EPR, designed to expose a contradiction. Take two particles, prepare them together so their properties are linked, then separate them by an enormous distance. Quantum mechanics predicted that measuring one particle would instantly determine the corresponding property of the other, no matter how far away it had traveled. To Einstein, this was absurd on its face. Either the particle already had its property the whole time, fixed since the moment of preparation, and quantum mechanics was simply an incomplete description that was missing some hidden detail. Or, the measurement here was somehow reaching across the universe and physically influencing the particle over there, instantaneously, which violated the speed limit relativity had only recently established as sacred. The original 1935 paper actually used position and momentum, not the spin or polarization examples most modern explanations reach for, because those were the properties Heisenberg's uncertainty principle was built around, and EPR wanted to attack quantum mechanics on its own signature turf. The core structure survives the translation perfectly well either way. Prepare two particles together so a specific relationship between their properties is fixed by the preparation itself. Separate them. And quantum mechanics claims that pinning down one particle's property tells you the others instantly, however far apart they've drifted. Einstein wrote to a friend that the whole idea amounted to what he called, in his native German, Spuckhaft Fernwirkung, spooky action at a distance. He meant it as an insult. He was certain that a deeper, more complete theory would eventually be found, one with hidden variables, secret pre-existing values carried along inside each particle, and that quantum mechanics would be revealed as a useful but incomplete approximation, the way Newtonian mechanics turned out to be an approximation of relativity. Niels Bohr, the leading defender of the new quantum theory, wrote a rebuttal, dense and philosophically slippery, essentially arguing that the question of what a particle is doing before measurement is not a meaningful physical question at all. The debate between Einstein and Bohr over this exact point simmered for the rest of both of their lives, and neither man ever fully persuaded the other. Here is the detail that stunned me when I first learned it. For nearly 30 years, this argument was treated by most of the physics community as philosophy, not physics. Interesting to argue about over drinks, irrelevant to actual laboratory work, because nobody could think of an experiment that would tell the two positions apart. If hidden variables were real, and if spooky non-local influence was real, both pictures predicted the exact same measurable outcomes. There was, everyone assumed, no way to test which one nature had actually chosen. There's a reason it took 30 years, and it isn't that nobody was clever enough. It's that the debate had been quietly reclassified. By the 1950s, quantum mechanics was already the most successful predictive theory ever built, correctly describing atomic spectra, chemical bonding, semiconductor behavior, and a dozen other fields to extraordinary precision. Physicists were busy using the equations, not interrogating what the equations were secretly claiming about the furniture of reality. The Einstein-Bohr argument got filed under interpretation, a section of physics polite people didn't spend career time on, because tenure committees and grant reviewers had no way to reward research into an untestable question. It took someone with an unusual amount of institutional slack and an unusual amount of stubbornness to pick the argument back up. Everyone assumed that until a physicist working essentially as a hobbyist on the question proved them all wrong. John Stewart Bell was a Northern Irish physicist whose actual day job was designing particle accelerators at CERN. The Einstein-Bohr debate was, by his own account, a side interest, something he thought about on his own time because the physics establishment considered it a closed, unproductive question. Colleagues who knew him described the paper he eventually wrote as something closer to a hobby he pursued during a sabbatical year, tucked in alongside his actual accelerator design work, not the kind of project that was supposed to reshape a century of physics. In 1964, working mostly alone, Bell did something nobody had managed in 3 decades. He found a way to make the philosophical argument mathematically testable. Bell's insight was to stop asking the unanswerable question of what a particle is doing in the moment before measurement, and instead ask a narrower, sharper question. If hidden variables exist, if each particle secretly carries a predetermined answer for every possible measurement someone might eventually choose to make, then there is a strict mathematical limit on how strongly correlated the measurement results of 2 separated particles can ever be. He derived in inequality, now called Bell's inequality, that any theory built on pre-existing local values, values that don't require any spooky influence, could never violate. Quantum mechanics, when you run the actual calculation, predicts a level of correlation that breaks Bell's inequality, not by a little, by a specific, calculable, testable margin. For the first time since 1935, there was a real experiment on the table. Measure the correlation between entangled particles carefully enough, and you could find out, empirically, whether the universe was built on hidden pre-existing values or something genuinely stranger. This is worth sitting with for a second, because it's the hinge the entire rest of the story turns on. Bell didn't prove entanglement was spooky. He proved that spooky and merely secretive were, for the first time, distinguishable by experiment. Before Bell, both explanations were equally untestable stories. After Bell, one of them had a mathematical ceiling the other one could break through. Let me give you a rough feel for where that ceiling actually sits, because the number itself is what makes this a real experiment rather than a philosophical shrug. Picture two detectors, each independently choosing one of several possible measurement angles for every incoming particle, run over thousands of trials. If the particles are carrying secret, pre-written answers, sealed envelopes prepared back when they were created together, then basic probability sets a hard limit on how often the two detectors can agree across all the different combinations of angles they might choose. Bell's original derivation, and the cleaner version most experiments actually use today, worked out by John Clauser, Michael Horn, Abner Shimoni, and Richard Holt in 1969, produces a single number, a maximum correlation score that any sealed envelope theory can never exceed no matter how cleverly the envelopes are written. Quantum mechanics predicts a score that sails past that ceiling, not infinitely past it, by a specific, calculable margin, one you can write down before ever switching the equipment on. That's the entire structure of the test. Build the machine, run the trials, count up the score, and see which side of a hard mathematical line the universe actually falls on. Before we get to the experiments that actually broke that ceiling, I want to hand you a picture, because the words entangled particle don't mean much until you can see the actual weirdness happening. Forget particles for a second. Picture a single coin, spinning in the air, caught in that blur where you genuinely cannot say whether it's heads or tails, because it hasn't landed yet. Now imagine, through some impossible trick, that spinning coin gets split into two spinning coins, both still midair, both still unsettled, and the two of them fly off in opposite directions, one toward Earth, one toward the edge of the galaxy. Here's the part that separates this from an ordinary magic trick. Right up until either coin lands, neither one has a value. Not a secretly decided value, you simply don't know yet. No value at all. Genuinely undetermined, the way a question hasn't been answered because it hasn't even been asked. The moment the coin on Earth lands, say it lands heads, the coin at the edge of the galaxy lands tails. Instantly, no matter how much distance sits between them. Not because a signal raced across the galaxy to tell it what to do. Because the two coins were never two independent things pretending to coordinate. They were one single shared system the entire time, described by one single mathematical description, and separating them in space never separated them in identity. Landing one is, in a very real sense, the same event as landing the other, just observed from two different locations. That is entanglement. Not a signal, not a message. A single shared indeterminate state, wearing two separate locations. Real experiments use particles instead of coins, most commonly photons of light or electrons, and the property being measured is usually something like polarization or spin rather than heads and tails, but the coin captures the essential shape of the thing perfectly. Two outcomes, correlated instantly, with nothing that could reasonably be called a message traveling between them, because there was only ever one system to begin with. You can even build the pair in a lab without much exotic equipment, conceptually speaking. Fire a laser into a specific type of crystal, and every so often the crystal converts one incoming photon into two outgoing photons, lower in energy, whose polarizations are linked by the same conservation laws that govern the single photon that created them. Send one down an optical fiber to one detector and the other down a different fiber to a second detector, however far apart those detectors happen to sit, and you've built the exact spinning coin situation described above, just made of light instead of metal. The crucial word in that whole picture, the one Einstein's camp bet everything on being false, is undetermined. Einstein's version of the story kept the coins already decided the instant they were created, just hidden from view, like two sealed envelopes carrying pre-written answers. Bell's inequality is the tool that lets you tell a genuinely undetermined shared coin apart from two sealed envelopes with matching pre-written answers, purely by counting up enough results and checking whether the correlation crosses a line that sealed envelopes could never cross. Push the coin picture one step further. because there's a detail that trips people up constantly, and it's worth getting right before we move on. It's tempting to imagine that once one coin lands, some kind of instruction physically zips across space to force the other coin to land the opposite way, arriving instantly, breaking the speed limit in transit. That framing, harmless as it sounds, sneaks the very thing Einstein was worried about back in through the side door, and it's not actually what the mathematics describes. There is no instruction traveling anywhere. There is one wave function, one mathematical description, spanning both locations from the moment the pair was created. Landing the first coin doesn't send anything to the second coin. It simply completes the single shared description that already, structurally, included both of them. Distance never separated the description in the first place, so there was never a distance for anything to have to cross. Bell published his theorem in 1964. It took years for anyone to actually run the experiment with enough precision to mean anything, and even longer to close the loopholes skeptics kept, quite reasonably, pointing to. The first serious attempt came from John Clauser, working with Stuart Friedman in 1972, using pairs of entangled photons generated from calcium atoms. Their results violated Bell's inequality, favoring quantum mechanics over hidden variables. But the experiment had gaps. The detectors weren't efficient enough to catch every photon, leaving room for a skeptic to argue that the photons which happened to get detected were a biased, unrepresentative sample. The experiment most people actually point to as the turning point came a decade later, in 1982, from a French physicist named Alain Aspect. Aspect's team closed a specific gap, known as the locality loophole. The concern here was subtle but important. What if, somehow, information about which measurement setting was chosen at one detector managed to reach the other particle before its own measurement happened, through some ordinary, non-spooky physical process, sneaking in at just under the speed of light? Aspect's setup switched the measurement settings so rapidly, using acousto-optic devices, that no signal traveling even at the speed of light could get from one measurement to the other in time. The correlations held anyway. Bell's inequality was violated, cleanly, exactly the way quantum mechanics predicted. There was still one more loophole standing, called the detection loophole, essentially the same efficiency problem from the 1972 experiment. What if the detectors were still only catching a specific, biased subset of pairs? Anton Zeilinger and various collaborators spent decades pushing detector efficiency and experimental design further. And in 2015, 3 independent teams, working with electrons and diamonds, with photons, and with atoms, simultaneously published loophole-free Bell tests. Every remaining reasonable escape hatch for local hidden variables was closed, all at once, by 3 separate groups using 3 completely different physical systems, all agreeing with each other and all agreeing with quantum mechanics. Worth pausing on how deliberately paranoid this whole process was. Physicists spent decades trying to defeat their own result, not confirm it, because the claim being made was extraordinary enough that any surviving loophole, however small, would have been a legitimate reason to keep doubting it. The locality loophole assumed a hidden signal moving at or below light speed. The detection loophole assumed a biased sample of only the easiest to catch particles. There was even a third, more exotic possibility called the freedom of choice loophole, the unsettling idea that the random choice of measurement angle at each detector might secretly be correlated with the particle's hidden properties from the moment of their shared origin, perhaps all the way back to some common cause in the particle's shared past. Experiments addressed this one too, using randomness generated from the flicker of distant quasars, light that left its source billions of years before either detector existed, specifically so that nothing inside the solar system could plausibly have conspired to rig the choice of angle in advance. Every one of these loopholes got its own dedicated experiment, its own dedicated fix, and every single time, quantum mechanics won. In 2022, the Nobel Prize in Physics was awarded jointly to Alain Aspect, John Clauser, and Anton Zeilinger, specifically for these experiments. The Nobel Committee's citation is almost startlingly blunt for a scientific body. Experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. Nearly 90 years after Einstein tried to use this exact scenario to prove quantum mechanics incomplete, the Nobel Prize in Physics was handed out for proving him wrong about it, using the very thought experiment he invented to make his case. I want to be precise about what got settled and what didn't, because it's easy to overstate this. What got settled is that local hidden variables, sealed envelopes with pre-written answers, cannot explain what these experiments observed. What remains genuinely open and is still actively argued about among physicists and philosophers is exactly how to interpret that fact, what it says about the deeper nature of reality. Nobody disputes the data anymore. People still disagree about what the data means. Before we get to the part everyone's actually here for, it's worth knowing this isn't a settled, dusty corner of physics people stopped poking at once the Nobel Committee made its call. Entanglement research is one of the more active frontiers in experimental physics right now, and the records keep moving. Distance is one obvious axis. China's Mischius satellite, which we'll come back to shortly, distributed entangled photon pairs to ground stations separated by well over 1,000 kilometers, something that would have been laughably difficult with ground-based fiber alone, since ordinary optical fiber loses too many photons to noise and absorption over those distances. Ground-based fiber networks have their own competition running in parallel, with entanglement distributed over hundreds of kilometers of deployed telecom infrastructure in China, the Netherlands, and the United States, each pushing toward what researchers call a quantum internet, a network where entanglement itself, not just encrypted classical data, becomes the resource being routed from node to node. Scale is a second, genuinely stranger axis. For decades, entanglement was something you produced and measured in single photons, single electrons, single atoms, systems small enough that quantum weirdness felt quarantined to the subatomic world. That quarantine has been breaking down. In 2021, separate research teams demonstrated entanglement between macroscopic vibrating drumheads, tiny mechanical membranes visible without a microscope, thick with trillions of atoms, entangled with each other's motion the same way a pair of photons can be entangled with each other's polarization. It's not remotely at the scale of a coin or a cat, but it's a serious, measured step away from treating entanglement as something reserved exclusively for the smallest possible objects. Number of entangled particles is a third axis, particularly relevant to quantum computing. Google, IBM, and other groups have pushed genuinely multi-particle entangled states, tens, and then low hundreds of qubits linked together in a single coherent system, each additional entangled qubit making the overall system exponentially harder to simulate with an ordinary computer. None of this changes anything about the no communication result we're about to walk through. More distance, more mass, more particles doesn't loosen that constraint even slightly. What it does mean is that entanglement has gone from a delicate laboratory curiosity, barely surviving long enough to measure, to an engineering material physicists are learning to manufacture, extend, and network on purpose. The spookiness hasn't gotten any less real. It's just gotten a lot more useful. So here's the part almost no popular explanation actually walks you through, and it's the entire reason for this video's title. If the correlation is real, instant, and confirmed by 3 separate Nobel-winning experimental lines, why can't you use it to send information faster than light? Go back to the spinning coin. You have one coin, someone on the far side of the galaxy has the other. You watch your coin land. Say it lands heads. You now know, with certainty, that there's landed tails the instant yours landed, regardless of distance. That feels like you've received information. Here's the catch that breaks the sci-fi version completely. Which face your own coin lands on is random. You do not control it. You cannot force your coin to land heads to send a 1, or tails to send a 0. All you can do is watch what your own coin randomly does, and infer what theirs randomly did. Randomness cannot carry a message. because a message requires the sender to choose the content. Push a little further, because the real experiments are slightly more interesting than a single coin flip. In an actual Bell test, each side doesn't just measure a fixed property. Each side independently chooses which property to measure, for instance, which angle to check the polarization at, and quantum mechanics predicts specific correlations that depend on the relationship between the two chosen angles. This is where people's intuition tries to sneak a signal back in. Surely, they think, the person on the far side could infer something from the specific pattern of correlation based on what angle their partner chose. They cannot, and the reason is beautifully simple once you see it. Look at the results from just one side, in isolation, ignoring the other detector entirely. What do you see? A string of outcomes that is completely, statistically random. 50% heads, 50% tails, no pattern, no structure, nothing that depends in any detectable way on what angle the faraway partner chose to measure. The correlation only becomes visible when you compare the two lists of results side by side. And comparing two lists requires physically bringing that information together, which means sending it by ordinary means, a phone call, a radio signal, a data cable, something bound by the ordinary speed limit. Take away that comparison step, and each individual observer is left holding nothing but a meaningless string of random static. Let's make this fully concrete with numbers, because, trust me, it's random can feel like a dodge until you see the actual figures. Say two experimenters on opposite sides of a lab or opposite sides of a planet are each measuring the polarization of one photon from an entangled pair, each independently choosing between a small set of possible measurement angles for every incoming photon. Look at only one experimenter's notebook, ignore the other entirely, and you'll find each measurement came back as one of two outcomes roughly half the time, in an order that passes every statistical test for randomness anyone has ever thrown at it. Change what angle the faraway partner happened to be measuring at that exact moment. Rerun the same analysis on this experimenter's notebook alone, and the 50-50 split doesn't budge. There's no dial to turn, no signal encoded in the choice of angle, no fingerprint left behind in the local statistics. The correlation is real, and it's also completely invisible until someone puts both notebooks on the same table. This has a name in physics, the no-communication theorem, sometimes called the no-signaling theorem. It is not a rule bolted onto quantum mechanics from the outside to prevent embarrassment. It falls directly out of the mathematics of quantum theory itself, provably, the same way Bell's inequality fell out of the mathematics of hidden variable theories. You can prove, using nothing but the standard equations physicists already use to predict entanglement experiments, that no operation performed on one half of an entangled pair can change the statistics an observer measures on the other half, unless the two of you compare notes through an ordinary classical channel afterward. Sit with the shape of that result, because it's genuinely elegant. Quantum mechanics is simultaneously the theory that predicts correlations strong enough to break a mathematical bound that no classical, common-sense theory could ever break, and the theory that mathematically guarantees you can never exploit those exact correlations to send a message. It's not a coincidence or a lucky accident that these two facts sit inside the same framework. They are two faces of the identical underlying structure. The randomness that makes entanglement look spooky is the exact same randomness that makes it useless for communication. Remove the randomness, and you'd also remove the correlation strong enough to break Bell's inequality in the first place. You cannot have one without forfeiting the other. Nature seems to have built this with a kind of built-in insurance policy against exactly the sci-fi trope I opened this video believing in. If entanglement can't send messages, you might reasonably ask what all the fuss over quantum information technology is actually about, because it is a real, well-funded, rapidly advancing field, not a purely academic curiosity. Start with quantum key distribution, sometimes called quantum cryptography. Here, entanglement isn't used to send the actual secret message. It's used to generate a shared secret key, a string of random digits, in a way that makes eavesdropping detectable. Two parties measure entangled particles, then compare a subset of their results over an ordinary classical channel, the normal internet, to check for the telltale statistical fingerprint an eavesdropper's interference would leave behind. If nobody tampered with the particles, both parties end up holding a shared random key that nobody else could have secretly copied, because the act of measuring a quantum particle unavoidably disturbs it. In 2017, China's Mishia satellite distributed entangled photon pairs between ground stations more than 1,000 kilometers apart, generating secure cryptographic keys used, among other things, for an intercontinental video call between the Chinese and Austrian Academies of Sciences. The entanglement did not carry the video call itself. It carried the key that locked the encryption, protecting an entirely ordinary, light speed or slower data transmission. Since then, the same basic architecture has been extended into a broader push toward a genuine quantum internet, ground stations, and orbiting satellites acting as relay points that hand off entanglement from node to node the way ordinary internet routers hand off data packets. Except what's being relayed is the raw correlation itself, still useless as a message, still entirely dependent on an ordinary channel to become useful. Then there's quantum computing, where entanglement is doing something closer to its truest job, acting as a computational resource rather than a communication channel. A quantum computer's power comes partly from entangling many qubits together, letting the machine explore an enormous combined space of possibilities in a single operation, in a way no arrangement of independent, unentangled bits could replicate. This is why certain problems, like simulating molecules for drug discovery or factoring extremely large numbers, are expected to become dramatically faster on a sufficiently large quantum computer. None of this involves sending information anywhere faster than light. It involves using entangled qubits as an internal resource, all sitting inside the same machine, or connected by ordinary channels between machines. Even when separate quantum processors are linked together, forming what researchers call a modular or distributed quantum computer, the entanglement between chips has to be established and later read out through the same ordinary, classical, light-speed-bound wiring as everything else in the room. The advantage isn't communication speed. It's the sheer size of the mathematical space a fully entangled system of qubits can represent, growing exponentially with every additional qubit, in a way that ordinary independent bits simply cannot match, no matter how many of them you have. And then there's the concept that confuses people more than any other: quantum teleportation. The name alone does most of the damage. Quantum teleportation is a real, experimentally demonstrated protocol, first realized in 1997 and since extended to distances of hundreds of kilometers, including between ground stations and satellites. It transfers the exact quantum state of one particle onto another distant particle, destroying the original state in the process. It sounds, from the name, exactly like the Star Trek transporter. It is not. The protocol absolutely requires sending two ordinary classical bits of information by conventional means at or below the speed of light from the sender to the receiver, without which the receiver's particle is just useless noise, correctly correlated in a statistical sense, but impossible to decode into the original state. Teleportation without that classical channel doesn't work. It's right there in the mathematics. The same no-communication theorem showing up again in a different costume, guaranteeing that even this genuinely remarkable protocol can never outrun a phone call. Here's the mechanical reason those two classical bits are non-negotiable, because it clears up a lot of the confusion in one move. When the sender performs their half of the teleportation procedure, called a Bell state measurement, on their particle together with the one whose state they're trying to send, the outcome is one of four possible results. And which of the four you get is random, decided by the measurement itself, not chosen by the sender. Depending on which of the four results came up, the receiver's particle ends up holding the original quantum state either exactly as it was, or rotated in one of three specific, fixable ways. The receiver has no way of knowing, on their own, which of the four cases applies to their particle, because from where they're standing, all four look statistically identical. The two classical bits are the sender telling the receiver which of the four outcomes happened, so the receiver knows whether to apply a small correction. Skip that message and the receiver is left holding a particle that's correct only one time in four, indistinguishable from the other three cases without the note that came by ordinary means. The teleportation in the name refers to the state moving, not the information about how to read it. And that second piece is exactly the part that has to travel the slow way. Every real application of entanglement, every one physicists have found in 90 years of trying, either uses it as a shared resource sitting inside a system that's already connected by ordinary means, or explicitly requires a classical, light-speed limited channel to be useful at all. The instant, unlimited range correlation is completely real. What it correlates is randomness, and randomness, no matter how perfectly synchronized across any distance you like, was never going to be able to carry a message. That was never the part that was broken. That was always the part protecting relativity from the one thing that would have genuinely broken it. There's a related piece of quantum mysticism worth clearing out before we close, because it usually rides in on the back of the communication myth. The idea that consciousness itself, a human mind paying attention, is what triggers a quantum measurement, as though the universe is somehow waiting for a person to look before it commits to an outcome. This shows up constantly in pop science retellings of the double-slit experiment and gets bolted onto entanglement almost automatically, since both involve the word observer. Nothing in the mathematics of quantum mechanics requires a conscious mind anywhere in the process. What triggers what physicists call decoherence, the process that turns a delicate quantum superposition into an ordinary, definite outcome, is interaction with a large, complex environment. A detector, a stray air molecule, a photon of light bouncing off the particle. Anything that entangles the original system with a huge number of additional degrees of freedom, scrambling the original correlation beyond any hope of recovery. A photon hitting an unmanned, unread detector in an empty lab decoheres exactly the same way a photon hitting the retina of a physicist does. Bell test experiments run for hours with nobody watching a single individual particle in real time. Results only tallied afterward, and the correlations show up in the data all the same. The word observer in physics papers is a piece of unfortunate historical jargon, inherited from decades of loose talk, and it means any sufficiently large, sufficiently entangling physical interaction, not a mind. It's a small correction, but it matters because it's the same instinct that produces the communication myth, the instinct to smuggle a person, a choice, an intention into a process that is, underneath the jargon, entirely mechanical. So let's go back to where this started, a Star Trek-flavored idea I carried around for longer than I'd like to admit, of entanglement as a magic instant telephone spanning the galaxy. Take that picture apart piece by piece, and here's what's actually sitting underneath it. Einstein tried to use entanglement to prove quantum mechanics was an incomplete, embarrassed placeholder for a deeper, more sensible theory built on hidden, pre-existing values. Bell handed the argument a mathematical spine 3 decades later, turning an unwinnable philosophical dispute into a number you could actually measure in a lab. Clauser, Aspect, and Zeilinger spent half a century closing every loophole a skeptic could reasonably demand, and walked away with a Nobel Prize for confirming that nature really does behave the spooky way, not the secretive way. And running underneath every single one of those results, baked into the same mathematics that makes the spookiness real, is a second guarantee, just as ironclad, that none of it can ever be turned into a message. That second guarantee isn't a footnote or a disappointing asterisk on an otherwise incredible discovery. It's the other half of the same discovery. The randomness that lets a pair of particles violate Bell's inequality is identical to the randomness that keeps them from violating causality. Entanglement was never a communication technology quietly hiding inside physics, waiting for someone clever enough to unlock its faster-than-light potential. It was always a correlation technology, a way of linking two genuinely undetermined outcomes across any distance in the universe, useful for cryptography, useful for computation, useful for teleporting a quantum state onto a new particle, and permanently, provably incapable of carrying a single deliberate bit of meaning without a classical channel walking alongside it the entire way. It's worth remembering, too, that the entire chain of reasoning that got us here started as an attempt to embarrass quantum mechanics. Einstein wasn't trying to discover something new when he co-wrote the EPR paper. He was trying to demonstrate that quantum mechanics couldn't possibly be the final word, that a more complete, more sensible theory had to be waiting underneath it. Bell picked up that attempted embarrassment and, without ever setting out to defend quantum mechanics, built the tool that would eventually confirm it beyond any reasonable doubt. 90 years later, the thought experiment designed to break the theory is the exact same thought experiment now sitting inside working satellites, banking-grade encryption systems, and quantum processors, and Einstein's name is permanently welded to the very phenomenon he was certain couldn't be real. That's not a footnote either. That's what it looks like when a scientist's objection turns out to be more valuable and more durable than the conclusion he was hoping to reach. If this rearranged how you think about the spookiest confirmed fact in physics, subscribe, because next time we're taking Bell's inequality apart line by line, the actual number that hidden variables can never cross, and why breaking it is one of the cleanest proofs in the history of science that reality itself refuses to keep its secrets fully hidden. We'll build the ceiling ourselves, from scratch, using nothing but basic probability, and then watch quantum mechanics fly straight through it. Einstein asked the right question. He just got the wrong answer. Next time, we do the math ourselves.